Ses, ses. 1, 2, 3. Geliyor mu?
Geliyor.
Tamam.
Ben yanlış bir şey söyledim yani en sonunda. Yani zaten çok anlaşılmayacak bir şekilde söyledim. O koalisyon kurulunu aynı değil. Değil. O sadece şey. İşte doğru. Oraya böyle onu oraya yerine başka bir şey yapmaya çalıştım ya. O yanlış. O en sondaki. Kafam gitmiş herhalde. Bilmiyorum. Tam alakası yok. Alakası yok. Yanlış. Ama şeyler doğru. Orada yapılan şey doğru. Orada yapılan şey doğru. O ikisinin arasındaki bağlantı o kadar direkt.
Test. Yeah, okay, great. Can you hear me?
And someone confirm that they can hear or they can't. You can? Yes. Okay. Okay, great. So Gonjan will be his second talk.
Okay. Yeah, so I will talk about this paper by Shanda Troyman Zaslow. Sorry, not Zaslow, Williams. This four has a, each three has a paper, so it's the Shanda Troyman Williams paper. Sorry. And the name of the paper is on the combinatorics. Bigger, sorry. So on the combinatorics of exact Lagrange surfaces. So I will start with actually explaining Weisschen-Handel attachment. So maybe that will be useful. Last time I didn't maybe say anything about this. So there is this property of Weisschen manifolds. If you are given a Weisschen manifold, you can attach a handle, Weisschen handle, to get a new Weisschen manifold. So let's say you have a Weisschen manifold. Still, and with Weisschen, then you can attach a Weisschen handle, we say. And in part here, actually, I will focus on. So let's say this Weisschen manifold has dimension 2n. I'm recording. Okay. So yeah. Okay, given Weisschen manifold, you can attach a Weisschen and handle, we say, which is T star dn. Okay, to this to get a new Weisschen manifold to get. Okay. So attachment happens along. So attach along infinite boundary of M. So do you recall this? Remember, for Liouville manifolds, we have a boundary at infinity, or we could cut Weisschen manifold as a, I mean, we can express it as a Weisschen domain, right? You could cut the cylindrical end, then there's a boundary. So that's called boundary at infinity, okay? So I will give an example, maybe you will recall that. So you attach this to its boundary at infinity. Attach along, not this, sorry. Attach along the boundary of distance, dn, which is Sn minus 1, which living inside boundary of m at infinity. And we remember, I also mentioned this is a contact manifold. And this is a Legendre. So maybe for that part, maybe I should say Weisschen comes with Liouville one form. Okay. And the contact form is just restriction of this one form to this boundary at infinity. Okay, so and the Lagrangian is just a subspace of this where this alpha vanishes. Okay, and the dimension is n minus 1. Okay, this is just the story. Maybe on example it will be more clear. So I will give some examples now. Okay. So example. So we know cotangent bundles, right? We know they are Weinstein manifolds. Last time we showed. If for let's say T star n and where n compact is Weinstein manifold. This is we discussed last time. So let's just actually work with T star S1. So T star S1 is yes. Let me color the skeleton different. Oh, okay, here. Maybe red is good. And maybe label vector field also. So this is X label vector field. And red is skeleton. And which is zero section, remember, for cotangent boundary is zero section. Do you remember this picture? So then the contact boundary is this part, these two. Right, okay, this is the contact boundary of this. I said M. Let's use M for now. Okay, yeah. Actually, sphere boundary. Because this is like a set of directions, right? You know, sphere bundle or co-sphere bundle, one can say. So this part, and this part. Okay, so now I can, from using this, I can construct new spaces. So how do I do that? So let's look at the description. So I should just choose some Lagrangians on this, in the infinite boundary, right? In the contact boundary here. But what are the Lagrangians here for this dimension? It's just points. So just choose. I should actually choose this circle. I mean, 2 points actually, because n is 1 here. So 2 points. I need to choose 2 points. Let's say I choose this 2 point. I mean, if you know Morse theory, actually, in general, I need to give some neighborhood of this also. I mean, you need to describe the framing, but in Weinstein story, you don't need to do this. It's automatic. So you just choose some Lagrangians and complete it to the disk D1. And then complete it to its cotangent bundle. So which is T star D1. So that's the attaching procedure. Does it make sense? And this has a Liouville vector field, of course, because it's also cotangent like this. But this Liouville vector field and this doesn't match, so you need to perturb this one. You kind of perturb it here a little bit like this. But that perturbation makes new skeleton, so kind of you complete this part of the skeleton. Liouville vector field. Just bring it down. Bring it this down. So this red part is the new skeleton of the new space. Then you need to perturb this layer also. So what is the space then? What did you get? Is it familiar, anyone?
We kind of hole.
So there is here one hole, there is one hole back, and one hole bottom. So 3 holes. Actually, we had this kind of example, three holes, a surface. Sorry? Pair of pants. Yeah, pair of pants. This is the pair of pants. Actually, the skeleton is exactly this thing that I mentioned, right? That same skeleton. If you look from some particular direction, I think.
It's a star and
This is cossphere bundle.
okay.
So tangent bundle is the set of directions, right? So set of vectors, this set of directions. So I kind of forget this. I'm divided by positive scaling, basically. So this is a pair of pants. Yeah, I will give one more example. I mean, basically this example, I mean, if you can get these examples, then just I will generalize this to dimension 2, whatever I say here. This is the dimension 1 skeleton, right? This paper happening in dimension 2 skeleton. So, but let's understand what's happening here first. So I can start with this system. Maybe I draw it too tall. Okay. This is skeleton. This time I will attach using 1 point here, 1 point here. I can do this, right? And this is D1. We call it core of the handle, actually. This core. And T star D1 is just draw a neighborhood. This neighborhood, again, uniquely determined by some stuff. Okay. And the new skeleton is, you bring this down like this, along the level vector field. And you kind of perturb level vector fields, etc. And this is the new, this new space after attaching this T star D1 like this. And what is this one? This space? Yeah, one puncture torus, indeed. So it's like a puncture torus. Yes. Etc. So now the thing I want to talk about is what are the moves so on this attaching. The thing is, I can, so this is Lagrangian, right? But maybe Lagrangian doesn't make sense too much. I mean, I just give this definition, but at least in this point case, if you move your Lagrangian along Lagrangian isotopy, which means if you move it with isotopy, which is through Lagrangians, the resulting space doesn't change. Okay? In this case, you can ignore Lagrangian. You can move this point like continuously or whatever, smoothly, and the resulting space won't change. Okay? So this is the actual idea. So through the idea, I can change the skeleton, which doesn't, and that won't change the resulting space. So let's do it for this one. Maybe for two.
You're following. So the handle attachment, but it's not just constructing a space, it's constructing this entire Weinstein structure. With the symplectic form, the legal vector field, then you can look at the skeleton, everything is happening here, all of that, not just spaces.
So all the substructures, so Weinstein, as I mentioned, manifold, we can get this. Okay, but I can attach. Okay, maybe I will work on this picture because of time reasons again. So I will erase stuff on this. Where the tracer? Nerede? Öyle mi? Nerede? Does this happen to anyone? I don't remember. Yeah. Okay. Okay, let's attach different way. Okay, so I won't attach it like this. I will attach like along this point instead. Just move, I move it a little bit. So as I told you, it shouldn't change the Weinstein manifold. Okay. But it will change the skeleton. So you will see. I get this skeleton. Okay. And I could also attach it here, then I would get the other one. So maybe locally, let's see what's happening. Okay. So just look at very local picture. So I have this skeleton, right? I'm just taking this strip, okay? I attach along here and along here, I get this skeleton, right? Locally. And I could attach here and here, I could get this one. So equivalent means the Weinstein manifolds are equivalent. They are different skeleton, okay? And I could attach to the right, I could also get this one. Okay. Actually, this is the idea of this paper, kind of. This is kind of this surgery in dimension one, let's say. I can get from this skeleton to this skeleton by moving like this. They seem like same, but so one, this is not same like them, but one last thing I want to say about this is what about sheaves on them? If you remember microcool sheaves, what happened to sheaves? So maybe I will use some very naive definition of microcool sheaves. Assuming that the skeleton is very stratified, you know, and everything. Microcool sheaves, you can think like on the smooth part, you give vector space, actually chain complex of vector space on smooth part. And a singular part, there is some maps going on. For example, how do we determine those maps? Like Vivek did last time. So for example, Vivek analyzed this kind of singularities, right? He analyzed that if you have this kind of singularity, you need to have I mean, there's convention, so I will use this one. So I will give A, B, and C here. Maybe I should write bigger. Different color. So there's A here. So every smooth part, by the way, this is wrong, okay? Every smooth part you give local constant sheaf actually. But assume, so it's all contractible. So every smooth piece of the skeleton, you give some vector space. Yeah, let's say like that for now. Vector space A, B, and C. Chain complex of vector space, actually. And the shape tells you the maps between them, kind of. So here you have this kind of map, here you have this kind of map. This is my last talk, I'm Vivek's talk, okay? So you can just take it as a definition. But and actually there is also something here, it's called microlocus talk.
Say a little bit more what you're doing. So now we have this space and we're trying to understand its wrapped Looijenga character.
Yeah.
Now it's equivalent to some kind of sheet.
Yeah, so I forgot to say which category I'm working on, right? So microcosm sheaves on this skeleton I'm working, okay? And it's equivalent to wrapped square category of resulting Weinstein manifold, okay? This is, I think, Vivek mentioned. Weinstein sector in this case, yeah, because there's a boundary. Boundary also there, actually. So I'm just giving you on this category an object, okay? Which means an object is actually kind of collection of sheaves on this part where there is some maps around singularity coming from microcosm sheaf geometry, which you need to work out. So this is not part of this talk. But there's also this X and Y part. Anyway, never mind those parts, but I mean, there's also
I think we don't have
stocks.
to rush so much. We
Yeah.
don't have to just let's work this out. I think
You-
without understanding this dimension, we won't be able to understand anything about four dimension.
You want to do shift theoretical understanding of this, or
Just we can say in the end the four-dimensional case is similar, and then
Uh-huh.
if people are interested, they can read the paper.
okay?
So
So
let's make sure that people can see what's going on here, because I think people are lost.
okay, so yeah, if you are lost here, so maybe we should stay here.
Yes.
Okay, so let's do this stuff.
Start from the beginning, from the picture, what we're doing from the picture. We have this skeleton, and from this skeleton, we're trying to determine this category of the whole thing, of this complicated manifold, punctured form. Okay, not so complicated, but kind of complicated.
Uh-huh.
We're trying to do that by piecing it together from we have smaller pieces, and we want to understand the small pieces, and then we want to kind of glue them together to get the big thing.
Mhm.
But now we're analyzing the small things.
Yeah, so actually I won't get the big thing, but just trying to say that even the small thing is different. Okay, so the shapes change from this skeleton to the other skeleton where you move this 2 point like that. Okay. Okay, so still, maybe I won't explain
But the
how.
category doesn't change, right?
Yeah, the
that's-
category doesn't change. So idea is this is a one object on this category, right? This object in this category will go to some other object in the same category. So it will go to different thing. So how I know that? So because first of all, this will give you a different representation of that same category. So this is the same as Michael Shears on this thing. Okay. So let's see so you can think this transformation like this. For example, when I move this part, so this is my shift, right? When I move this part like this, so assume I have some stalks here, A, B, C, X, and Y, right? This is my shift. And microshift will stalks are A, B, C, X, and Y. So when I move this, what about the stalk here? What will happen to that? I mean, it's not affected by anything, right? This part, this moves, and this stalk is still A. So this A. This is C, this is X, this is Y. Those are not affected by this. I won't discuss this category, by the way. So let's just go to the next picture. So you pass this picture, this will be still X, this will be still C, this will be still A. But what about the middle part? First of all, let's put a question mark here, but what about the arrows? What is the direction of arrows here in this side? If it's up, it's left direction, right? So here is down, so it's right direction. This opposite. Here's down, this is right direction, up, left direction. So first of all, arrows even flipped. Can I still put B here?
Here, like in directly, or
Sorry?
directly.
So this DG category. DG drive, do people call DG drive those categories? But don't think about, so those maps are not morphisms. Everything is a one object right now. Everything is a one. So think like this shift. What is shift normally? Shift is sections and restriction maps, right? Yeah.
Then the sheep responds to tolerance.
Yeah. So this category, this category is representation of this quiver. Okay. Forget about X and Y. We have A, B, C, right? So it's a representation of this thing, this quiver.
Yes. So
You mean ABC here?
Yeah, this question
So-
from also
Maybe let's think shift easier even, think like,
what's the mathematical definition at this point?
yeah, no.
I think people can understand.
Yeah, actually it's very simple understanding of the shift, right? What is shift? Stalks, right? Stalks and restriction maps, right? So think, I want to give a shift on this thing, right?
Not that thing on the line.
But
So it's almost like a sheep on this horizontal part of this, but it's a micro sheep. So it's a little bit different than a sheep on this, like in the back slope. It can jump along this vertical pieces.
Yeah, okay. You can also give the sheep on this whole thing, but since Vivek didn't say this, so I won't say this also. You give sheep here, and stokes are A, B, and C, and these arrows are restriction maps. Why there's no restriction map here? Because it's local constant there. It's just trivial there. So I don't have any arrow in this region.
Is it the local constant?
Local constant sheaf has just one stalk and monodromy. So if this is contractible, there's no monodromy. So it's just constant sheaf. So in this part, it's just contractible. So it's just constant sheaf. In this part, it's constant sheaf. In this part, constant sheaf. Yeah, but here it's not constant sheaf. Therefore, there's a restriction, non-trivial restriction map. But why this is only one arrow? And this is Vivek's talk. So we can discuss in discussion session if you like. Why at that point is one arrow.
Shift A.
Sorry?
What is the support of shift A?
It's A again. So I support, you mean, okay, this whole thing. Everything, it's not, never zero. Support is the part where it's not zero, right? It's a usual support. So it's everything. Okay? So make sense? Sorry?
They change, and then you change the category. So they only derive the category, right?
You mean this and this? These are DJ equivalent or derived equivalent also. I mean, whenever some two things are DJ equivalent, it's in particular derived equivalent. Okay?
So he's just saying, if you think of them as vector spaces, actual representation categories, they're not equal.
Yeah. So you should, you need to take a chain complex of vector spaces. And these are chain maps, actually. So that's what's going on.
So you need to take DG representations, and the category of DG representations of those quivers are derived.
Yeah. So
this is a correct statement?
Yeah,
I don't know.
I mean,
No, but it should be obvious from this picture because they're both modeling this category wrapped to that category. And that category is, it only depends on the manifold that this gives not the skeleton. So that's supposed to tell you that these representation categories are derived equivalent.
it is known from representation theory also, right? There's a sync moves. You replace sync with the source, etc. You know those moves? So I mean, from representation theory, we also know this is true. But anyway, from this also we can reprove that fact. So which means this representation theory and this representation theory, this representation category are the same. Okay. But this question mark, okay. So what is the stalk here now? Maybe I ask this. The thing is, I don't actually know answer immediately, but it's not B naturally, because now there's an arrow from A to something. So this is arrow from B to A, right? Arrow from B to A. This from A, so I don't know if there's there's no natural way of defining an arrow from A to B from this data. So this should be something else. This should be D. Okay, it can be determined somehow, but it's different. So just I'm trying to say this. Okay. So as you see, we get something different. And this part is different.
Which forms like X and Y differ from A and C. Can I think about and X and Y as like also sheaves?
If you remember, there was a micro stalk, right?
Yeah.
So this arrow uniquely determines a stalk here, but this arrow, this data determines it. We can discuss in the discussion section if you like, but there's a way to, that's how you will kind of figure out D, because you know the micro stalk should be X. And you should put something here such that, so that the micro stalk is X here.
But he also that the picture not equivalent by X and Y, so they're not, I don't know. They can't
Okay, so those are different moves, okay? So I mean, you are bending it, but those are different moves. So, but in short, let's look at this. If you look like this line and this line has a different shift on them, right? So they are different actually, this line and this line. Okay, they have different shifts on them, right? Okay, so yeah, sorry. This is X and this is Y. Okay, so probably
Those representation categories are not the same if you think of them over vector space representation. Isn't this like some theorem about you can change the if you have like you can change the arrow direction and the result the category with the next to be right? Just the right, it's only the right.
I mean,
Well, this only tells you right.
the reflection is the path and the source. The path of the reflection and the source is not just like there is an equivalence in the reflected panels in the point if all panels are coming to this point or they're all going. So yeah, so the one is the projected right and the other is the rejected right.
Yeah, but I don't know this very well. That's why I'm asking, because you guys could connect to what's going on from that perspective. That's why I'm pushing this. Okay, but you at least agree that there is a DG equal, like derived equivalence if you look at DG representations of these two categories. This we agree.
I mean,
So that's this statement. It's already kind of non-trivial, right? It's not already kind of, it's not.
I mean, there is a theorem in representation theory where if you have two trees and if you choose any source in that tree and just make the other arrows to go out of from source, their representations are DG equivalent. So this one instance of this. So there's a tree. I choose this as a source here. You can choose source or sink. So you can just choose sink, and they're DG equivalent. But kind of this is a geometric proof of that fact. Okay. So let's do the surface case. Okay.
The claim that attachment, after attachment, the perturbation is unique up to blah blah. And right.
So I mean, after you attach this.
I mean, Weinstein handle attachment is unique up to.
I mean, it's unique up to determining this Lagrangians. So once we determine those Lagrangians here, and it's up to their Lagrangian perturbation. It's unique. So.
And the perturbation data determines unique in this picture.
Yeah, perturbation data actually determines the map.
And
yeah,
ABC and
yeah. So this perturbation gives you some equivalence in the category level because it doesn't change the actual Weinstein manifold, so it doesn't change the category. So it actually gives the map. Actually, this described in the Guillermo Kashiwara-Shapira paper, how this determined, how this move determines the actual shift, how actual category moves. So they actually study this. So anyway, any other question? So we can do this in the also in higher dimension, right? So let's say take T star surface. Let's call it surface N now again, or let's call it M, and M is surface. And compact surface, okay? Then you can attach handles to this and to get a new manifold. So the dimension of this is a 4-dimension, right? Because surface is 2-dimensional, is 4. So you can attach this study too to this one. And maybe I just give you an example. Yes, I don't have much time, so let's just focus on examples, right? Easy to understand. So let's say M is surface, torus. So this T star torus, okay? And this is the skeleton part. So it's T star, this is the Weinstein manifold. Then you will say this, okay, how can I attach this to this? Boundary of T2, so which S1. So I need to give S1 on where? In the in the infinite boundary of this T star torus, which is the sphere bundle of the torus. The sphere bundle. And what is the co-sphere bundle? Again, points on this with directions, right? So I cannot draw this cosine bundle right now. But instead I can specify this circle. So this should be Lagrangian actually. Lagrangian. I can specify this Lagrangian on this cosine bundle just looking at the torus, this M. So there's T star M, right? Up. And there's S star M actually. So again, what are the points of the cosine bundle? Points on M with direction. So for example, I can just draw a circle. This is a curve on M. But if I give a direction at each point, what is this? If I give direction at each point, it is actually not a subset of cosine bundle. And there's one more thing, which is to be Lagrangian, this direction should be perpendicular to your curve. That's Lagrangian condition, okay? So I cannot choose any direction. I need to choose a direction which is perpendicular to the curve. So there is actually two choices. Either I will choose this direction at this point or this direction. So therefore, so this S1 can be described like this. The attaching circle can be described by a circle, simple closed circle, curve, you can say, and a direction, perpendicular direction. Let's say this direction. So I will just draw hairs, okay? So now maybe let's stop. Does it make sense what it means? So this is actually a subset of cosine bundle because at each point I'm giving you a point on M and a direction. So it is actually a subset of cosine bundle for this reason. And it's S1 and Lagrangian condition is just this direction should be perpendicular to your curve, which is satisfied. So this actually I'm just giving you as exactly this one. Then you attach T star D2 to this thing on the cosine bundle. Okay. Of course, I won't be able to draw actual picture because it's higher dimension, right? But this is the just the way I can draw it here.
Maybe you can give like the exact thing here, like what is this picture in this dimension?
Yeah. So for example, this circle here, I mean, this M here is actually corresponding to here. M is here. And I could actually give this data how? I could give this data without actually drawing this part, right? I could give a point and a direction. Here, I could also do the same thing here. I could say, okay, this is point and this direction, and this point and this direction. If I do this, what this means? This direction means up. So it means actually I am looking at this point, but in this cosine bundle, in that direction, which is this point actually. I'm meaning by this point and this arrow, I mean this point. By point and left, I mean the point at the bottom. Okay? So this actually corresponds to this data, which tell you which point you should attach your handle. Okay? So basically, then you attach a disk to this thing on the cosine bundle, and you then kind of complete it to T star D2 and get a Weinstein manifold. Does it make sense? Okay, so let's attach one more thing. I mean, I can attach not just one, I can attach multiple, right? I can attach this one more, like this. Okay, so how much time I have? 17 minutes. Maybe this is simple. Maybe I will just work with two curves. And I will say what happens with this. So now maybe now let me tell the goal of this paper, okay? So the paper says this determines the Weinstein manifold. Do we agree with this at least? So because Weinstein manifold, T star torus, and I give you some handles. So it gives a new Weinstein manifold, right? So this paper gives some combinatorial or like a moves on these curves, okay? So it will give some moves and it will change the collection of this curve to new collection of curves. Then the claim of this paper is, so let me tell you actually this move. So this paper says this. So let's say this is the curve 1, C1, this is curve 2. Okay? And let me actually follow my picture because otherwise I will mess up. Okay, maybe let's from now on focus on the analysis so that I can draw everything easier. So the thing that this paper does is this. So it will define a mutation on this curve, so such that it will change this collection of curves to new collection of curves. Okay, so I will first show you how this mutation works. And since this mutation works, so let's say if I do mutation at C2, it just do change this collection in the neighborhood of C2. So I can just focus on neighborhood of C2. And neighborhood of C2 is just analysis. So from now on, let's work with analysis. There's this analysis. And there's this C2. Okay. Actually, let me say this is C3. Let's say this is C1 and one more color. C2. Okay, I kind of cut a piece of this. So I just cut the neighborhood of this blue curve. So let's say there's one more curve here. So let's say this is C3 and this is C2. Okay. I just look at the neighborhood of C3. So it's neighborhood of C3. I have this picture. So there's a mutation operation on this. So mutation at C3. Okay. So this mutation does the following. The first of course, C3, it just changed the orientation. We call this pincer orientation, okay? So instead of this way, C3 becomes that way. Okay, it does this to C3. So C3 prime now, this new curve. C1, so if the intersection is this way, so you can just look at the intersection number here, the positivity or negativity by right-hand rule. So this fin is going up, blue fin is like this. So with right-hand rule, this is positive. So it's positive intersection, we say. Positive intersection. So this negative intersection, this opposite, if you look at it, this is like negative. So at negative intersection, it doesn't do anything. So this curve just stays as the same. So C2 prime is just C2 actually. At positive intersection, here, it does it dan twist on this curve. It does dan twist. Like this way. And the orientation is the same. Okay. Yeah.
So we draw now. So in last minutes, the space T star M, right?
So no, T star, actually this is T star M is this white part. Okay. T star torus actually. Whole space is T star M. union T star D2 corresponding to C1, you know. So let's say times 3, let's say. So I attach T star torus, 3 T star D2, sorry. So I mean, I start with T star M, so coordinate bundle of torus. Then I attach 3 disks to that, so I get a new space. So it's no longer coordinate bundle; it's something else. Like in this example, right? It was T. I'm sorry.
Do we have as Lagrangian subspace our initial?
Great remark. Yes, indeed.
Okay.
So that's actually part of the paper. So we want to understand that Lagrangian. I'm sorry.
We choose now another one's Lagrangians, which is C1, C2, and C3.
So we attach new Lagrangian disk to that. Okay, and it becomes a singular Lagrangian. If
Okay, but it's still like a Lagrangian.
There is a unique choice for the frames to make it Lagrangian, right?
yeah, so true, but that's not actual thing. So this is the resulting thing is a skeleton, right? And skeleton itself is Lagrangian for Weinstein case, exact Lagrangian. But this torus is still sitting inside your Weinstein manifold as a exact Lagrangian itself. Okay, so it's still inside your Weinstein manifold.
That's the question. So you take this, for example, C3, you say, right?
Oh yeah.
But in the left-hand lower plane, you also did some kind of mutation, but the mutation was kind of relative to 2 of these things, right? But I mean, these are equivalent. So
Yeah. So this mutation actually. So let me find the analogy between this. Actually, this analogy is this. Analogy is converting these blueprints this way to this way. This is the analogy here, not the intersection part. So, I mean, for this, what happens to C3? Directions reverse, right? So that kind of mutation happening here. Maybe two of them, let's say, both of them. Both of them. The pair of them, I mean, pair of them is better word, yeah, pair of them. Because pair is the here, yeah, exactly. So, I mean, pair is the, so here S1, here are the circles are object, there is the 2 points are object, right? The pair actually, I mutate there, so the arrows rotate. So that exactly corresponds to C3 here. So I mutate C3, the direction reverse. Actually, that's the, I want to focus from after this picture, if I have time, and just do analogy between those picture and in this C3 picture, okay? But let's maybe, at least combinatorically, I mean, you see, right, a priori, this is a completely different picture, right? Not super completely, but I mean, it's different picture. So it would give a different Weinstein manifold, you would say. So this is a new Weinstein manifold with different new Weinstein skeleton. But the result of this paper is this. It says these 2 Weinstein manifolds is actually the same. It doesn't change the Weinstein manifold. So this just generates a new skeleton.
So without C1 and C2, just reversing the pairs of C3, you get the same Weinstein manifold, right?
I mean, yeah, with C1 also, I mean, all included.
Without C1.
Without C1 also is still true. Actually, that's the actual part. Sorry?
This is the right method.
Oh, yeah. So C3 case is this. And actual mathematics is actually happening here. C1 and C2 is not that important, actually. It just follows from, I mean, if I can draw the picture for C3, it's not that hard to prove this result. Also, I mean, if you do this, it doesn't change. Actual part of the proof is just reversing this C3 doesn't change the default. But let me, since I give you some remarks on this, if you
Once you make the statement, so you need to change the C1, right, to get the same manifold. You can't just reverse the arrow of C3. You need to.
No, of course. I'm just saying this. If you just work with C3 and nothing else in this picture,
Okay, if there's nothing,
else,
other curves that you use.
you still change, then it's true, right? But if you attach this, you need to change the C1. But that change is kind of forced by this move. I mean, this move force your C1, it kind of automatically does this move to your thing. I mean, basically just proof voice on the.
Knowledge here would be to, so you have the 2 points, which is S0 and S1, and you change the orientation. So instead of taking the inward pointing ones, you take the outward pointing ones. Co-orientation, outward pointing arrows. And that kind of, you can also realize that change as moving one on top of the other.
Yeah.
And that's what you did here.
Yeah, and here also same, just higher dimensional version. Actually, nothing different here, and not nothing different, but it's just higher dimensional version of it.
Sorry, may I ask a question?
Like just on torus, just take appropriate, I don't know, do we have some Lagrange form? Just, I don't know, without these 2 additional dimensions. Because we have 2 cycles and cycle A, cycle B, and
You mean cycles are this? You mean?
yeah,
Okay, which space are you taking? What is your?
just
Yeah, any M you say.
and just like a torus without T star.
Okay, but that is what we watched in manifold. I mean that will be different story. I mean, you can make it Weissman manifold like
2-dimensional example. Why do you want to take a torus? This is the 2-dimensional example. Then in one higher, so this is S1, that's S1 cross S1. So here you take an S0 inside S1. There you take an S1 inside S1 cross S1. Something like that. I mean, so
just without,
So is there an isotopy that takes this picture to represent?
yes, exactly. So, but there's some tricks. But that's the idea. There's a Looijenga isotopy you can do, and you end up with this kind of curves. So therefore, it doesn't change the Weissman manifold, but it changes the skeleton. But why changing skeleton is important? I mean, it's important, of course. I want to generate lots of skeleton. One other thing is this. This skeleton has this torus as a subspace, right? So there's this torus in this skeleton. I mean, this torus. So when I mutate, I create the same Weissman manifold using a torus again, using these curves. So I mean, let me say again. Okay. So I have this torus and this curves, right? Now I mutated. I get a new torus and new curves. I won't draw all of them, but at least draw this one like this, etc. Okay. So now I claim this, right? So this both create same Weissman manifold when you do attachment, but different skeleton. But the thing is, this torus doesn't correspond to this torus anymore. How do you understand this? Maybe this shift understanding may help. Okay. I mean, there's a way to distinguish these 2 torus by looking local systems on them. You can distinguish them in the category level. So they don't correspond to the same object in the category anymore, in the Fukaya category. So when you do computations. So that's a computation part. You do micro shift.
Statement. I think you just have to say the statement clearly because I don't think people understood the statement.
Statement is this. This torus here and this torus there now living in the same Weissman manifold, right? Because they give the same Weissman. So between Weissman manifold, and it's so, and there's S living in this Weissman manifold, the surface, your torus, and the other torus living in the same Weissman manifold. These 2 Weissman manifolds are isotopic, actually you can show, but not Hamiltonian isotopic. So symplectically they are not the same. So you get a different actually torus. So what does it say?
So what do you mean about different torus? You mean that the image of the torus under this map is not a torus?
No, this is not the image of that torus. This is a new torus. This is not image of this torus. So I'm not saying this torus is exactly this torus. It's not happening like this. So this Weissman manifold doesn't construct same. I mean, there's some moves involved there because you are not using actually same torus. If it, it's not that maybe it's so easy thing.
Except that we take that these two Weinstein, the fact that these two Weinstein domains are symplectomorphic, let's just take that for granted. Okay, let's say that's a difficult theorem. Okay, let's take it as a black box. And then with that, then you can understand, because it's impossible. I mean, you feel like people will just look and understand. It's impossible.
Okay.
It's possible to understand why that's true. So let's just assume that you know, for some reason, someone told you that those two pictures define to you the same Weinstein manifold. There is an isomorphism between the two. But the point is that that isomorphism doesn't take the first torus that you started with to the second torus that you ended up with. They're different. Now you can think of these two tori living in the same space, and they're different. They're not Hamiltonian isotopic to each other. It's kind of like, again, finding different toric models, finding different C star squares inside your Looijenga interior, or cluster, right?
Yeah, so that's the actually, I mean, there are two things comes out from this. One is this mutation operation gives you new torus, right? I mean, since we're working with torus here, it gives you different toruses each time you mutate. So you can mutate this again, right? You can mutate this again, you get a new different torus. Actually, all of them will be different, assuming something. So you can actually generate infinitely many tori in some cases, okay, via this mutation. So you just, assuming your mutation doesn't repeat, you don't come back to the same curve collection, you always produce new tori this way. And if you know about cluster theory, local system on this tori actually gives you algebraic torus, okay? Maybe, so you're actually giving a chart on the Fukaya category or microcurve category. So, because, I mean, you are giving...
In the mirror, right? In the mirror.
It's not in the mirror only.
It's included thing, right?
But of course, the presentation is again, like, depends on your seeds, like kind of your starting data. But the object is a global thing. So let's say a very simple example of the relation between the associated cluster variety and the Weinstein manifold.
So it's like this. Let's take microcurve category of Fukaya category, okay? Fukaya category of your Weinstein manifold, or microcurve on the skeleton. Okay. So first of all, those tori are part of the skeleton, right? Or you can think like this. Okay, this torus is part of skeleton, right? Would you agree with this?
Why don't you write micro sheets on torus?
Torus, yeah.
No, and that's it, right? And that's it.
So this is local system. It's difficult to explain on the microcurve side. And maybe it's better I do this because
you took micro-local sheets on skeleton, and then you write local systems of torus embedded into that, something like that, right?
oops, yeah, sorry, I get it wrong. This, which is spelled. So the skeleton we just torus in disk, and torus embeds into this, right? Therefore, microcurve on the torus embeds into microcurve on torus union disk. But what is microcurve on torus? And there's a fact which, if you have smooth thing, microcurve on that thing is just local systems on that. Therefore, just local system on torus embeds inside this. But there's the other torus, right? The mutated torus. Local system of mutated torus prime, let's say, also embeds to this thing. And if you compute local system of torus, actually it's representation of pi1 of the torus. So it's actually algebraic torus, let's say. Anyway, so T, and this T prime. So the algebraic torus embeds into microcurve category. So kind of I'm giving a chart of torus in my microcurve category. But furthermore, I know how these two surfaces related their local system related. How I know? Because I don't know actually right now because we didn't do computation. But from this thing, you can actually compute how this and this related. There's a map between them. I mean, this story, I mean, how to say, they have some intersection and there's a kind of transformation. I mean, there's a map from this to this when they intersect. And that map is actually, this paper shows, is cluster transformation. So it's like this. You start with that surface in this Weinstein manifold. It gives you an algebraic torus chart on the microcosheaf category. So you mutate it, you get a new chart, algebraic torus chart on this microcosheaf category. And this first chart and second chart related by cluster transformation.
That's the variety to once a manifold, there are different objects which are related by this story.
Yeah, so it's not like a cluster structure of Weinstein manifold, it's cluster structure of Weinstein, Foucault category of Weinstein manifold. So it's not like Weinstein manifold has a cluster structure here.
Oh.
Yeah.
It actually does. But so then you can also start with the cluster, but just the leaves of the cluster variety, the X cluster variety. And you can consider this imaginary part of omega symplectic structure, and for some certain choice of omega, if you choose the right leaf in that deformation class, then that symplectic manifold is actually this kind of symplectic manifold.
Okay, but then you ask to this, you get another class of structure which could be different after, right?
A priori, yes, but it's not all. But here you're only using the symplectic structure, some kind of shadow of this whole symplectic structure on your cluster array. On the other side, you're actually seeing it as a cluster array, like with its complex structure.
I think that this example is also simple from the Foucault category point of view. So we just replace, so C1 prime is just a cone of morphism between C1 and C2. And we have zero morphisms from C2 to C couple to C2. That's why it doesn't change C2. Replace C1 by the cone of morphism from C1 to C2. It is a point of view from the Foucault category, I think.
Yeah, I mean,
It is just it happens.
Let's just say it's a good conjecture.
yeah, I mean, I'd like to think about this because I didn't understand right now.
If C2 was, C3, I don't know, was a spherical object, like that's the cycle that's there. But this it is not.
No, you have to be careful. You have to be careful.
I mean, maybe I can tell you what, I mean, I'm over time. Last thing, we should analogy like this. So what you do here in this skeleton, there's a disk, right? D1 here, actually here. There's a D1. You kind of contract it and recreate it, right? That's the move. That's actually called disk surgery. This move. You contract this disk and recreate it. This surgery. So actually, you do the same thing here. So, I mean, actually, C3 is not good here. Maybe let me erase C3 and just do it with C1. And let's save this mutation at 1. And that I finished. Not this color, but anyway. Okay, let's say we have just one curve. The C1 is just this way. And the mutation, if you are mutated at C1, it's this way, right? Just change the orientation. And the move is this. So this C1, you attach a disk on this, right? So let's say that disk is here. Maybe this is not a good explanation. Now I kind of already regret explaining this. Anyway, so there's a disk attached to the C1. So actually there's a disk somewhere here. So you contract that disk to a point along the way. Then you recreate that disk. Which recreating that disk is kind of, you change like that. So this is a new disk actually. So this attached disk is now new disk. This is the analogy between this and that. So that's actually proof. So maybe geometrically. This is called this surgery. Anyway, so maybe I should finish. So.
You said there's a legendary identity between the two, let's say, C bonds.
Yes.
It's part of it, but now you say that you pinch this.
So that pinching can be seen as a Legendre isotopy. So very quickly, let me show you this picture. I mean, at some point, I cannot show the whole picture, but maybe from my note you can see, but at some point you come to this picture where there's this plane and there is this thing, which has this circle up. And then this is a co-sphere bundle here. So using the contact form, contact form makes this goes this way. I mean, that's the, Legendre isotopy, sorry. That's the Legendre isotopy. It makes this circle smaller. So it makes it smaller, so it makes it like this. So if I watch the movie, this up gets smaller. So therefore this also gets smaller. So it makes it even smaller. At some point it becomes a point. Point with all the directions actually. And it becomes a point. Then it re-expands. So it's like the points are actually, there's a circle, all points are coming to the origin. Then they pass the origin, right? So they are going to the other direction. So now they re-expand. Therefore, now they are looking to this direction. So they are going to that direction now. It's growing like this. Actually, it's exactly same as this picture. So not exactly maybe, but this surgery can be realized by Legendre isotopy. I do Legendre isotopy. On the skeleton, it does this surgery thing.
But in this picture, during the isotopy, X and Y, they come to the same vertical fiber.
At some point.
This is
that's also happening there, but it's like this. At here, it has all the directions, right? What is the thing? What is the thing which has all the directions? It's just fiber, cotangent fiber, if you think. So actually, pictorially, at that point, it becomes this. Plumbing sector, we call it. That's the intermediate step for dimension 2. For dimension 1, this was cross. Dimension 2, what is cross? Zero section and fiber at origin, right? In dimension 2, same picture. Zero section and fiber at the zero, which is this. The same picture happening. But this circle is not like this. It stays like on the origin. It's not like staying like this on the co-sphere, but it stays like this. Just auto origin. So then it resolves again. So then it becomes this again. So the picture is this. This one comes to this, then that. Sorry.
And this Legendre isotopy does not extend to a Hamiltonian isotopy.
No, it extends.
But you said that these Weinstein manifolds are isomorphic, but not through Hamiltonian isotopy.
But the thing is, that surface is not that surface. So that's the thing. So it's a little bit strange part. I agree. Right? Because I'm not drawing. This picture is not that picture, as you see. This is actually not that picture. That was annulus. There is no annulus here. So because I did something to annulus first to create this new picture. So I kind of first carried that picture to this picture, then do Legendre isotope on this picture. But this is not the original picture. So there's some steps which is not apparent here. But you can see me in my lecture notes, or you can ask me if you want to see big full picture. So. But that's the actual invariance. That's the actual thing that happening here. This move here change structures. that singularity happening here. Yeah.
Okay, other questions? Online questions? Okay, let's thank one.
Thanks.
Um, 45 minutes. 1:30.